Class 11th, I am taking the new chapter, the chapter number 9, that is the work, energy and power. So first I will take the work. Whenever the work is to be done, then definitely some force is applied on the body. So the body gets displaced. So because of that displacement, that work is done. Suppose you take the body and lift it to a height of 1 meter, or you carry the body from one place to another place, or you just stretch something and compress something and just you push it and pull it. That some work is always done by the force. Whenever the body is getting the displacement due to the force. It is defined as the product of force applied force and displacement of body in the direction of applied force. So if the displacement is being done by the force, then there is the work. If no displacement, then no work. So this work equal to force into displacement in the direction of force. Direction of force. So now we are having a body here. This is now surface and this is a body. This is the body. Let some force is applied on it. This is now force F applied on this body, and as a result this body gets displaced in the direction of this one. So now let this makes an angle theta with the horizontal. This is making an angle theta. Then we will have the two components of this one. This is now your F cos theta, and this component the F sin theta. F sin theta. The body will be displaced due to this F cos theta, but this F sin theta will give no displacement to the body in the horizontal direction. And let this body is displaced to a distance x. Suppose this is I am drawing the next figure. This is the body. The force is acting on it. Then the body is getting displaced. This is getting the displacement. Let this displacement is x from center to center. This is now your center and this is also the center of this body. Then this distance is between the centers of this body. So this we take that x is the displacement in the direction of the force. Let a force F acts on the body at an angle theta with the horizontal. With the horizontal. The component F cos theta will produce a displacement x. So the work done, this is equal to now your this F cos theta into x, or this work done is denoted by W. So W, this is equal to F x cos theta, or this is equal to F dot x. This is equal to W. This means what? That the scalar product or the dot product of the force and the displacement is equal to the work done. The scalar or dot product of force and displacement is the work done. Is the work. So you can have that depending upon this angle theta, this burden will be positive, negative and 0. So for theta equal to 0 degree, it means what? That the displacement is parallel to the force, or x parallel to the applied force. Then this W is equal to Fx cos 0 degree, and this gives W equal to Fx. This is a positive work. So this W equal to positive. So this is whenever a constant force acts on the body, then whatever the displacement is there, that you find it. So you can have, this is now suppose here we have this y direction, this is now your x direction, this is now 0, here we will have the force, this is now displacement, this is a constant force is acting here, then this is now suppose the displacement x here, then what we have, this area that will be equal to the work done. So W equal to area under fx curve and x-axis So this is now rectangle. Then we can have that this rectangle is equal to this length into the width. So this so much is the force F here that is applied. This is now F. Then this displacement is x. So length into breadth. This will be equal to the work done. And now we'll have this for theta equal to pi by 2 or 90 degree. It means that the force is applied in the perpendicular direction. The displacement is produced in the perpendicular direction of the force. So this is how. Suppose this is a body. This is the body. The gravitational force is acting on it. The weight mg, and body is getting displaced in this direction. This is now suppose x. Then definitely this angle is equal to 90 degree. So we are adding to this. This is x, this is f, then this angle is equal to 90 degree. So when the body is pushed or pulled on the surface, then work done by the gravitational force is always equal to 0. W equal to fx cos pi by 2. So this is equal to 0. This work done is equal to 0. So it means that now here we have x parallel to f, and in this condition here we are having this x perpendicular to f. So work done by the weight is equal to 0. When a body is pushed on the horizontal surface, the work done by gravitational force is 0. And now for theta equal to pi or 180 degree, it means what? That this x is anti-parallel to x. So angle between them is equal to 180 degree. So this is suppose we are having this a body. This is now suppose ground, and a body is lifted from here to this distance. Then definitely a weight will be acting here. Weight mg. Now this is moving in this direction, so displacement will be in this direction. This is now your x, and f is vertically downward. Now you have here that for this one, this W equal to fx cos pi. So this W equal to minus fx. This is a negative work done. it is negative burden. It means that burden may be positive, negative and 0. So how to help to this one? Now you can show it by the graph. Suppose this we are having the work done W, and this is now suppose we are having the theta on this axis. Then on 0 this will be now work done equal to so much, and then this, and then this. So what we have, this is now your 0, this is pi by 2, and this is pi, and this is now your 3 pi by 2. So now this burden is to be positive, negative here, this is now negative, minus W, and here this will be your plus W, and here this W is equal to 0. It means that the burden can be positive, negative and 0. So for this negative we will have example. Body is carried vertically upward. The work done by gravity is negative. Carried vertically upward, the work done by gravity is negative. So this is, we have taken a force which is acting on the body. The force is constant. If suppose the force is variable, for variable force, now what we have, this is now suppose x, this is now suppose your y. Here is the force F that is applied to here. Force, this is now displacement x, and the force is like this. Then what we have, this is now suppose x1, and this is now suppose x2. Then we consider a small element of this one. This is now like this. This is now let dx, and this is now force F here. If the force is variable, now consider a small displacement dx due to force F. Then the area of this one, this is strip. Area of this is strip. Suppose this is now your A dash, B and B dash. Then work done equal to area of A dash, B dash. So this is equal to what? F into dx. F into dx. So So now what we have, suppose that displacement is from x1 to x2. For displacement from x1 to x2. Now this is now work done dw. There are so many like this segment. So if we add to all these segments, the area of all these segments, that will be equal to the work done from this point A to the point B. This is now point A, this is now point B. Then this W is equal to integration x1 to x2 f dx, f dx. If suppose you are given the dot product, then you can have to this like this one. So this will give you the work done. So if you are given the limits and the force F is expressed in terms of x, you can find the work done with the help of this integration. So we can have that the integration over the fx curve represents the total work done under this area, under this curve AB. So this is how to find the work done by the force acting on the body. When the force is having this constant magnitude, then there is no problem. Just you find, then just you take the product. That will give you. And if suppose we are having the variable force, then this x will vary as the function of x. The force F is the function of x. So this x, F will vary according to this x. Suppose you are given f equal to 3x, x equal to 3x square, 4x, like this, then you can just you differentiate to integrate to this one and find the work done. So this is about the work done in this chapter. So this is very important one, and that I will tell you about this, the unit of this work done. Now unit of work done. Unit of work. Now as we know that this W is equal to F dot x. So F is measured in Newton, this is in meter. So in MPS, this is now your Newton meter, or this is equal to now joule, J, joule. So what we have, the relation is that 1 joule is equal to 1 Newton meter. It means that if 1 Newton force produces a displacement of 1 meter, then burden will be 1 joule. If 1 Newton force produces a displacement of 1 meter, the work will be 1 joule. Now this I am taking in MKS and then in CGS. we are having this dyne centimeter, and this is also called the erg. So now we are having this 1 erg equal to 1 dyne centimeter. 1 dyne centimeter. It means that if 1 dyne Newton produces a displacement of 1 centimeter, then this will be equal to the 1 erg. If a force of 1 dyne produces a displacement of 1 centimeter, the work will be 1 erg. This is not definition of 1 erg. Now there is a relation between these two, that this 1 joule is equal to 10 raised to the power 7 ergs. 1 joule equal to, or we can have this 1 Newton meter equal to 10 raised to the power 7 dyne centimeter. This is also. And now if you want to find out this dimensional formula, then this will be m1, l2 and t minus 2. So this is the dimensional formula of the work done, and this is the relationship between the joule and the erg, Newton meter and dyne centimeter. And this is the definition of 1 joule, this is the definition of 1 erg. This generally asked in the board exam, that define the 1 joule of the work or 1 erg of the work, and what is the relation between joule and erg. So this is the short questions to be asked. And also this is asked that when the force is variable, then write down the formula for finding the work done. So that you write to this one, integration x1 to x2 f dx. So this is about the work done. So thank you very much.